let's start. I'm going to show you now the instrument. So we are connected to the instrument there. Last night we ran two samples. Okay, one is our reference material with a silica lumina sample. Another one is a zeolite sample for her. Okay, so we got some results, which I would like to show and share with you. Okay, and see how we can connect and we can select the correct limits for the BT surface area and everything. Okay. It is so easy with a microactive, with a program, with a system. It's so easy to adjust the limits. Okay, you don't have to make any calculation. You will see it just adjust the limit on the screen, and automatically the new numbers come out. Okay. So I'm going to show you first. This is the first sample. So you go to File. Let's move it too much. I hope it's not going to fall down. Okay, go into File. Open one of the files, and I think this is your silica lumina. This is our reference material.
Yes, the other one.
Okay, let's go to the other one first. Let's go to the zeolite.
It's called the Manal zeolite. It's the second, yeah, the second on that.
Okay.
This is the highest.
Okay, I cannot get better than this. So what we know is the first thing we should know is that zeolite should give us type 1 adsorption isotherm. Some of zeolites, depend on the way how been treated, can create some mesopores or can create some macropores, okay, or can create a false pores. What does mean the false pores is that because the zeolite is very fine particle size, very, very small particle size, okay? Then you can imagine that you have all these particles get together, but we cannot see that between the particles there's small distances, okay? And they can create very small pores. But they are not micropores, but they are large pores. When we do the adsorption, nitrogen will absorb any place which has a capillary or something empty between particles. Does not know if it's real pores or is interparticle pores. Okay, so in this case, we had the same configuration. Let me see if I can see it here. No. Okay, here at the end of if we have something as large pores or interparticle pores, can be seen only at very close to 1 relative pressure, pure P0, 1. Okay, in this case, as we're closing to 1, that's what I'm talking about is here, somewhere here. Oh, sorry. I'm dummy on this is why my son does everything for me. I don't care about these things here, okay? So you can see here it's not very nice because only 3 points. So the software does not know how to make nice curve because only what it does is just okay, this point to this point and this point to this point. But if we had more points, we will see nicer. But what is important is that the volume, okay, this point is the volume, higher volume, something has been absorbed here, okay? But we don't know what it is. But we are scientists, we need to know. We need to know what it is, because is it macropores, large pores? It is interparticles, distances, I need to know. How could I know if it's large particles or not? If it's macropore samples, macropore very large pores, okay, I should go to a different technique called mercury pore symmetry. But we don't have a mercury pore symmetry here, and I need to know what's going on here, okay? What I can do, I think this samples, I compact it, I form pellets from it. So some pressure on it. If it is interparticles volume, when I compress it, it's going to disappear or going to get much smaller. So this can tell me if it gets smaller, this is distance between particles. Okay, so it's not pores, so I can avoid it. But if it's really large pores, I cannot compact it, because I'm just only compacting a little bit. So I don't change the macroporosity. It's still the same. Okay? So this is the only way I can tell is it a large pores or it is interparticle pores. Okay? The system just absorbs, does not know where it is.
Sometimes with the particles of this zeolite, you have like cavities on the particle. So it doesn't have a smooth surface if you see it on SAM.
It could be like a cracker, for example. Could be. Yeah, could be.
Cavities.
Could be.
Okay, so if all the samples samples are smooth, we cannot see this.
Yeah, it could be, but it's, I suspect to be interparticles volume, okay? So with, as I said, if you compact it a little bit, then, because if you like to explain this to somebody, okay, it's going to ask you what it is, okay? Then you have to have an idea. So, but the only way, the easiest way to do it, don't go to any place else, you just compact it a little bit. If you compact it, then you can reduce it, then you know it's interparticles, very easy. The second thing is that we have seen many of our customers, I would say maybe 85%, they don't use very pure or high purity gas, especially for the free space with helium. They can have some oxygen. And because when you go from 99.99 to 99.995, you pay 3 times more, okay? So it will get very expensive. In some places, they cannot afford this because it's very expensive. So what we did, so they come to us, how we can do, because you know, if I don't have very well good free space, you're going to have negative adsorption. So what does mean, especially when you have type 1 adsorption isotherm, where it's steady, small change of free space is going to go down. So if the isotherm goes down, it's against the law. Okay, why it's against the law? Because the adsorption isotherm only can go flat or high, cannot go down. So cannot be desorption during adsorption. Okay, so we did something to avoid this problem. How can I see what is here? Down.
Press on the flag.
Okay, here. Sorry, thank you. If I go to the adsorption isotherm, the first thing you have to see on the plot or the report is adsorption isotherm. As I said, from it you can get everything you want. Okay, if I go to the measured adsorption isotherm, for example, the measured adsorption isotherm was 69 or 74. Sorry, 74. You got something like that. This is this morning when I came here, I got this, and this does not surprise me. Okay, because I said is 85% of the people they get something like that. So they came to me, or they came to us to Micromeritics, said, you know, we cannot buy pure gas, and you're telling us it's a free space. How do you know if it's a free space? If it's a free space, if I correct the free space, I should get good adsorption isotherm. If a problem with the instrument, you cannot fix it. It is anything you do, it's going to go down like this, okay? Because you cannot change the volume adsorbed. What you can change only the free space, okay? So how do I know if really free space or is instrumentation problem? If I change the enters instead to calculate it into free space to enter free space, you have warm and you have at 77K. Okay, the system has to know the free space of the sample tube empty at room temperature, and the volume at 77K will goes up. Okay, so this is very important for the instrument. Every time measures the volume absorbed, has to know what is the volume, empty volume for the tube, or what is the volume of gas absorbed. Remember, as I told you yesterday, we inject this amount of gas, and after equilibrium, this is what is left. So we measure the difference between what we dose it and what is left. We don't have anything inside the system. If you have, for example, gravimetric technique, then you can see the weight, okay? Because the sample is gonna be it's gonna absorb the nitrogen, and the weight is gonna go up, okay? Then you weigh the amount of nitrogen absorbed. In this case, what we do, we don't weight, we don't know how much absorbed in the sample, but the difference. We know how much we dosed and how much left, and the difference is the gas absorbed. Okay, so this is the way in the volumetric technique. Then the free space becomes very important for us. Okay, so now in this case here, I don't know, is this a problem with the instrument or is it a problem with the free space? So what's happening is this is, during the warm free space at room temperature, nothing's happened. But when you raise the temperature, the dewar, and the temperature get to 77K, is almost minus 200. If you have impurity in the helium, it's going to condense. The helium does not condense. If it does condense, then your free space is going to go down, because when you go from gas to liquid, is less. Okay, it affects your free space. So I said, okay, let's see if this is free space or not. This is 74, what we measured. So I go, for example, 75 or 73. It's still down. Okay, I go to 70, still down. I go to 69, still down. I go, you have about minus 20 plus 20 only. This is your limits.
What is the value you are changing?
The free space, not the volume absorbed. You cannot change the volume absorbed. The only person can change the volume absorbed is me. Okay, because we don't allow the people to play with the volume absorbed. Then start reporting things false. Okay, nobody can change the volume absorbed. Okay, but we can change the free space. Then I go to 68.
We calculated the value and we change it.
No, you just take is entered. You have measured, enter, and calculated.
Yes.
Okay, calculated we don't know because we don't know the density of the sample. Okay, so what I do is just measured. Okay, just enter. Just you may change only, as I said, in the cold one, not the warm one, because nothing's happening in the warm one at room temperature. Nothing's going to condense. It's only on the cold one where the condensables can take place. Is the oxygen from the air, okay, from the helium. Then you can go, for example, 65. Okay, you see it's coming up. Then you see it's a free space. They're going to go to 64. Okay, this is one. I know now I come to my experience. This is an ISS and zeolite type 1 adsorption isotherm. Means that I have to have a flat type 1 adsorption isotherm is a flat. Okay? I can just leave it, for example, 63.8 or 60.9. What's the point here? 0.9. Okay, 60.9 too much. It's raised, so I need to go down. Still too high, so 63 only. It's too high, so 64. Okay, wait, 63.9. Okay, no. Okay, this is the best fitting. Okay, if I was able to do it, means was my free space, and the free space directly related to the purity of the helium. Okay, as I said, if you go from 99.99 to 99.999, it's 3 times more expensive. Also for us in Micromeritics, and I have the people just in front of me who does the gases. Okay, I want the liquid argon. 1 hour later, I have it in my lab because they're in front of us. I like to have helium or hydrogen. They're in front of us. We're lucky on this. Okay, but in any case, not many people, especially in South America. In South America, we are very poor people. Okay, you cannot imagine every time they buy something, they beg me to give them 50%. Sometimes I give him for free, okay, because they'll have no money. I have now a case in Peru. Is a good friend of mine. There's just in the Andes Mountains, nice university. They broke a sample tube, which is glass sample tube, which is $110. They could not buy it, so I just send them 2 because they're students and they have to finish. They just talk to me. I give them two sample tubes. Okay, but I gave you 3 here, so you. Anyway, so this is the result. The second thing is that we need to have the weight. This morning he was upset because we saw the sample, the BT surface area was 0.6 or something like that. Okay, remember the specific surface area is the area divided by the sample weight. So the sample weight should be taken after analysis. Okay, why? Because the sample is clean and the nitrogen is already dissolved, so the sample is very clean. So we adjust this for the sample weight, and we get, if we get here to the BT surface area, okay, it says we have slope as intercept C value, and then you have to adjust the BT surface area for the coefficient. The computer is okay. You have 1019 square meter per gram. This is what we're expecting, very high surface area materials. Okay, so how can I adjust for the best limit for the BT? It's very important. Okay, you see here, for example, this is the limit, lower limit and higher limit. I can change the limit here. Okay, I can change, for example, here. Okay, if you go here, you get 713 square meters. You lost 300 meters square per gram, just because you did not have the correct limits for the BET. You see how important it is. Okay, so you don't rely on the instrument. The instrument gives you any number, does not know what the limits are. Okay, now we are working on a smart software. The smart software may become next year, and you will have it for free. It will adjust automatically, give the best fitting, which should be easy. Okay, start moving the limits until you get best fitting was 99.9999. Okay, so in this case, is our C value is negative. Remember what I told you yesterday? C value should not be negative. Means that we have a big error on the skins here. So now let's adjust the.
What is the value of the fitting now? What is the value of the fitting?
The fitting is if you count for the coefficient is 0.99, but you can see it's a Rouquayrol, so it is negative. Okay, Rouquayrol, as I said yesterday, is #1 in the whole world on the BET surface area. Okay, Mr. Rouquayrol, Monsieur and Madame Rouquayrol. So this, as I said, I spent with them six months, and it's very well known. They have many books on gas adsorption. Okay, so many people say the limits. I said, well, this is difficult to find the limits because in theory we have between 0.05 and 0.3. We know that we have from the monolayer, the multi-layer, until you set the condensation. Remember also yesterday I told you in the adsorption isotherm, you have the first inflection point where the monolayer finish and start the multi-layer, and the second inflection point where the capillary condensation starts. Okay, so this is our limit, but depends on the size of the pore. Could be, for example, my limit sometimes 0.2, 0.3, I don't know, 0.25. Then the Rouquayrol wrote a very nice equation to tell you where is your best fitting. Okay, so now I come to Rouquayrol and said, okay, Rouquayrol said here's negative, then I need to adjust it. I'm not very good on this. Let me see if I can catch it. Here. Okay, then I have to come in the positive, this one here. Okay, and the straight line. Okay, you can see here, for example, you have the straight line, and you get 0.9999, and you see C value 155, it's positive, and you get 1019 meters square per gram. This is the first thing you have to adjust. Why? The BET is the total surface area of your sample. Okay, but what we do have in our samples, we have a micropores. I need to have the micropore surface area. Yesterday also I told you we have no way to measure the micropore surface area. Some people they use the Langmuir surface area for the micropores, but the Langmuir more for chemisorption than the physisorption. The people don't like it, don't like this one here. So we adjust the BET limits to get a C value positive. In this case we got it very nicely, but sometimes you still have a negative, so you have to go lower on the low end. So in this case here you have 0.005, 0.05, you go maybe to 0.04, maybe to 0.03 until you get the first number C positive. You stop there and they get your surface area. In this case we have 54, perfect. Okay, so you get 1019 meters square per gram. Now I'd like to see what is the contribution for the micropores and what is the contribution for the mesopores. Okay, so what I have to go from BET to the T plot. Remember what I told you yesterday? The T plot is going to give you the micropore volume and the micropore surface area. Okay, how do we get the micropore surface area? From the slope of the T curve, we get the external surface area. And I said the external surface area is the area of the mesopores, and the difference is the micropore. So what we expect here? Okay, we should expect high micropore surface area and low mesopore surface area. Now if I get the reverse, something wrong. Okay, you see we have to think a little bit, not just rely on the instrument. If the instrument gives me more mesopores than micropore, something wrong with my limits. Okay, so let's see what the T plot gives us.
Here we adjust the limits just on the
Rouquayrol.
And then the other two are automatically adjusted.
Is automatically adjusted. Okay. All right, I need to go down now. Huh? Yeah. Still, yeah. Where are you? Yeah, where we arrive?
الويندو تبع هيدي عبد كنت عامل لها ماكسمايز، يعني اطلع لفوق بالارو لفوق.
هيدا
لا ما
هيدا علي هون هيك
ما بقى تطلع.
صار كله مضبوط. ضفيت طلعت.
Okay. Now we got the t-plot analysis, okay? The t-plot analysis, how we select the limits. Our first goal is the first inflection point, okay? Where the first layer is finished and we start the multi-layer analysis, okay? Where my first point here is here. This is my limit. Okay, I can go with here, but I'm not going to go lower because it starts going down, okay? So my inflection point is when finished. This is the first layer. And the second layer is just, I can adjust it from here, from the adsorption isotherm. Okay, you see how I can expand it there? See, but in any case, it should be a straight line. Okay, so the monolayer, multi-layer, and then condensation. Okay, so any point in the straight line is your t-plot analysis. Okay, so we have a good relationship. So you can see the correlation coefficient here is 0.9993. Okay, and it tells me the micropore volume is 0.27. How can I get the micropore volume? Is here, is this value here. Okay, but remember what I told you yesterday. The instrument calculate the amount of gas adsorbed. Okay, I said this is my volume this is the empty bottle. I will not fill it with air because I don't know what the volume is. So I fill it with water, and then I take the water to a gradual device and then measure how much the volume is. So exactly what to do is we use the curvature rules. I also showed you yesterday is a number. So we take the gas, amount of gas, and multiply by 0.0015468. Don't think I'm very smart. I just repeated many times, so I got it there, okay? But this is the conversion factor between gas and liquid for nitrogen. If you use argon, it will be different. Okay, for nitrogen is this number. So if you take this number here and multiply by 0.0015468, you get the micropore volume, the first number. Okay, so now from micropore volume, now I get to the external surface area by the slope. You see, you don't have to do anything. Everything is done here. Okay, and tell you the external surface area is 154. Correspond to what? To correspond to the small mesopores you have in your sample, but mainly should be a micropore area, okay? And the micropore area is 864 meters squared per gram is a micropore solid. This is what we expect. But if we have the reverse, we know this is a problem, okay? So surface area, so all the parameters you want, but what you do need here is just a micropore volume and a micropore surface area and external surface area. So what we have now, we have micropore volume, we have the total pore volume at the end of the analysis, we have the difference between them, we have the mesopore volume, we have the BT surface area, total surface area, we have the external surface area, and we have the micropore surface area. So we have everything, okay? Especially in this case, it's very easy, but when you have a bimodal distribution, it already has micropore and mesopores. It's very important for us in catalysis to know what is the contribution from the micropores and what is the contribution for mesopore in percentage. Okay, so I go to my t-plot analysis. My t-plot analysis will give me the micropore volume. I have the total pore volume at 0.99. I divide the volume of micropore by the total, multiply by 100. It tells me you have 80% micropore volume, okay, and 20% mesopore. So this is how you have to report it when you have a bimodal distribution. How much contribution you get from the micropore and how much contribution you get from the mesopores in volume and in area. Okay, then you are done. So you have everything. Then you go to the next point. If you have a micropore like this, you have no hysteresis. You have a small hysteresis here, and this is why you have external surface area. You have a small portion of mesopores, okay, little bit portions, okay, but the system will see it. How do we know if it is really mesopores? The hysteresis should close, okay. You can see it's going down a little bit and then close. If it's first, you see here, if it closed and then open and then close again, okay? If you had a problem with the instrument, once it comes down, it's keep going down, okay? Then you have a leak. Yesterday I also explained to you, if that desorption goes above the adsorption, you did not have enough time to take all the nitrogen out. So you absorb this much and you took only this. So what is the rest is inside the pores. So you need to raise the acceleration time. Unfortunately, you cannot do it here. You have to repeat your analysis. This was I said you for 15 seconds for micropore, for Mesopore and 45 seconds for micropores. Otherwise, you have to repeat the analysis. Okay? So this is the one. Second one is that if the desorption goes below the adsorption, so you took more than you put, you cannot do that. Okay, where is the rest is coming from? A leak. Usually the leak is come from the O-ring of the tube. Okay, if the ring of the tube is not well inserted, sometimes it's bent, it starts leaking from there. Okay, because you are making vacuum. Because when you do the desorption, you are applying vacuum to the system, so the air can come inside and you go below. Okay, but if it goes below, it's closed. Then go below, then close again, is a hysteresis. Okay, that's just in this case, a beautiful case in this case here. Okay, so you have a very small portion of mesopores, and the system you have 174 meters squared per gram. Okay, what else you can have?
Can you see the pore size distribution?
Yeah, this I'm going to go now. Okay, for the micropore size distribution, we need to have more points. Okay, so we need to have here, for example, I need to have more points, will be more sensitive. Okay, but we should see something.
So the first point is at what? 0.0 what?
This is this thickness, you have to see it on the adsorption isotherm. Okay, the first point is 0.005. Okay, this is, yeah, 20. This is our increment. This is what we put 0.005. Okay, the system, I will show you now how we print the sample. Yesterday I told you this is the only way I know if I have to have, if I can have points or not, is to know, have an idea about the volume. Okay, if my sample absorbs 0.005 and I put an increment of 0.05, you get adsorption with 1 point only. Okay. So normally we need to have an idea about the pore volume. What I do, exactly what we do in our lab, is take 1 point first at 0.3, okay, 0.3 where the multi-point finish, okay, and this gives you an idea about how much volume been absorbed up to 0.3. Then, okay, if my volume is at 0.3, 100 milliliters, I'll take 100 points. Then you get an increment 1. Every 1. You're going to get one point. So you get all the whole adsorption isotherm. In this case, we took 0.05. We didn't know anything. So you start at 0.05. The first point was too high. But if we took 0.001, we'd get 5 points before this. But if we get 0.00001, we get 10 points. Okay? But of course, if you go low, dosing, it's going to take much longer time, the system. Okay? Because we have 10 more points, and especially in very low end, it's a very small amount of gas goes to 10 to minus 4. Okay, so the system open and maybe too much gas, and has to take all the gas out and adjust the pressure. So it takes some time. So don't be upset if you have more points here. Can take 24 hours analysis. Okay, this is normal. Sometimes it takes 36 hours. As long as you have liquid nitrogen, the system is going to analyze. But if the system runs out from liquid nitrogen, there's a problem. You have to refill the system, or the system will stop, because the gas inside the sample tube is going to go up high, and the system is going to find out there's a lot of pressure. Okay, it's going to evacuate the system. Okay, so or it's going to pop up the tube. Okay, if it's during the analysis, it knows the pressure is too high, it will evacuate the system and stop. But if it's in equilibrium, during equilibrium, and the liquid nitrogen goes down, it's just in equilibrium, it does not open the valve, the sample tube, it pops out. Okay, we cannot avoid it. This is physical. Okay, so in order to avoid this long time analysis, we have to use a very small amount of sample. Okay, like in this case, we used 5 milligrams. Okay, this is why it's so fast. See? Even though we did not take this point, but it's finished during the night. We put it last night before we left at 7 o'clock, something like that, and this point was done. Okay, I was expecting to keep going, but it went very fast. Okay, so we could have done maybe 20 points and still done during the night. So in this case, it's lower the sample size. I'm going to give you a formula how to select the correct sample size. It's very easy. Sorry. You need to have an idea about the surface area of your sample. Maybe we don't know. We have no idea about what's going on, what the surface area is. But we have three categories of samples. Micropore sample, which is like, for example, silica, where the sample, the area is 100 or less. Let's see, for example, the maximum is 100 meters square per gram. This is the first category. If you have below this, you have no pores. Okay, for example, metal oxide, maybe 1 meter square per gram, maybe half a meter square per gram. You only measure the surface area with krypton with no porosity, only BET, because it has no pores. If you have pores, you have surface area. So the silica is the best case as for micropores materials, 100 square meter per gram. Okay, this is micropore. Yes, the other one is the mesopore, is up to 300 meters square per gram. It's just an example, okay? Just to have an idea, because at the beginning, give me a sample, just ask them what kind of sample is a micropore, mesopore, or micropore. Well, this is enough. And you have micropores, is about, I'll say, 800 meters square per gram, okay? More or less. Now, how much sample I like to have? My formula is meter square or square meter per gram times the amount of sample I need. This should be 10 or higher. Okay? So suppose I have 200 meters square per gram. How much sample I should take? Will be the mass in gram will be 10 divided by 200. This gives you about 0.05, right? I think it's correct. Okay? Gram or 50 milligram. So more or less take this one here and give me at least 10 meters square per gram. If you get less than 10 meters per square meter, 8 down to 5, it's just the limit of the detections. Means there's a small amount of gas being absorbed. So we're taking or we're losing sensitivity in the measurement. Okay? But you have 10 and higher, will be good. But I say, why I don't take it then 50? I can have 50, you have very good analysis, but the time will be 3 times more. So this is a compromise to get good analysis and not long time analysis, okay? If you get higher, 800 meters square per gram, you get maybe 20 or 0.010 milligrams, okay? So this is what we take, for example, 1,000, she took 5 milligrams, was correct, perfect, okay? Because it has a large amount of gas absorbed, so system is very, very sensitive, okay? This is why we got very nice absorption isotherm. So this is a rules. So this is just to make sure that we are taking the correct numbers. So please make sure you apply this. If you get less than 10, 5 or 4 or 3, you're going to get very bad results. So your absorption isotherm going to be like this, point like this, okay? Is because it's not sensitive enough to detect any change in the volume absorbed. Okay?
Okay, thank you.
Okay, let's continue with this. I'm going to go this way. BGH adsorption, okay? The BGH adsorption is for mesopores. It's going to give you anything. There's nothing there, okay? So I change from here. Okay, it tells you have small amount the porosity. Okay, it's very bad. This is the simulation. Okay, but for this is the delta V divided by delta log D. Okay, even though it's negative, but your porosity is a red one. It does not change, does not show any porosity there, but it's just a shape. Okay, so for example, I can change the limit. See if I can see something. Okay, you see the volume comes down because there's no mesopore. If I have a mesopore, we have very nice peak. Okay, it says just indication small portion of mesopore, but this is then I don't have pore size distribution, but I do have some external surface area. Okay, so this is indication of presence of some mesopores. So if you are interested in your reaction some mesopores, you have them, but if not, you only have especially the microporosity in your sample. Let's see if we have, for example, this is BGH because no condensation is taking place. Remember, the BGH only when you have a condensation. Let's see, for example, the DFT pore size distribution. We come here, it says a DFT, classical DFT. Okay, and this is the shape. You have in this case slit or cylinder. Remember, you need to download our program for all the models. Okay, so if I get, for example, cylinders and get the models is Halsey thickness. Okay, it shows you the micropores only. Okay, it shows a little bit here the mesopores, nothing, but only the micropores in your sample. Okay, if I take it like this, for example. Okay, this is your porosity here. Is about, this is your mesopores, 11.4, and if I go to micropore, okay, well, this is the regularization. The, well, anyway, I don't know what is showing the micropores here. It says 15 to 15 points calculated. Regular, don't see any pores here. Let's use this. Is it the model is not applying for here?
Where is the model?
Does not say any pore widths. I don't know why.
The model disappeared from.
No, here we are. Okay, 16 Armstrong, and you have very large pores. You don't have points here. Okay, but this is indication of very high presence of ultra micropores, because we don't have points. You don't see the curve, but you see here. What's indicating is you have very large micropores volume, which is we did not have the total, we don't have points. But we'd have something like this, but in large pores, in large volume. Okay, this is why it's so important to get so many points on a small portion of the pores.
What
okay?
is the number of points you advise to see this distribution?
The last point, where the first point was 0.05, and this is the first point. If we had 0.01, we would have 5 more points. If we get 0.005, we have 10 points. So we can see this curve very nicely. Okay, but let's see what's the.
16 Armstrong.
This is you have a bimodal distribution. You say the bimodal in your adsorption isotherm, you have a bimodal distribution of the micropores. Did you remember that? You see, if you can go, for example, the adsorption isotherm.
Yes, I have two categories of.
You see, one here and one there.
Yes.
Okay,
Yes.
and the system.
Armstrong and other is
11. Well, it's not well defined because we don't have many points.
So here what we get measured.
You get measured the 16, you can see it,
16.
and the other one was much larger in volume, much more, many other, but smaller than that one. But we cannot see it very well what size it is because they are not very well defined. This is the non-local.
I have more pores, I will have to.
More points.
More points.
Yeah. I'm going to take the non-local density function theory and see what it says. You have no models. We have no models in this case, okay? You need to download it. It says, let's see the DFT then. Okay. Let's see if I can get nicer things here.
How do you know which model to choose?
What's the proper model for zeolites?
is hexagonal. It's just like hexagon like this. Okay, we have model for that. We have for the zeolite perfectly. We have a different, I think at least three model for zeolite. Who asked which model we have to select? You? That's very good questions. When you select the model, okay, the system will calculate the volume according to the model. Suppose a cubic. We know for geometrically what is the volume of a cube by knowing the size of the pore by the Kelvin equation. Okay, so it will calculate for you for the density function theory is better because it calculates the size of the pore according to the density of the amount of gas absorbed. From the amount of gas absorbed, we calculate the heat of absorption, and from it we calculate the size of the pore. Okay, the diameters. Then we can calculate the area or the volume for a special pore shape. Then we make the cumulative volume for all the pores, okay, and we compare it with the total pore volume, was measured with nitrogen with modelless, no models, without any model, the correct volume. If these two volumes agree, then your models approximately is this one. If your model is the volume is different, then you have to change the shape of the models. Which, for example, go the cylindrical to slit-shaped pore. But we know, for example, in zeolite is more cylindrical than slit-shaped pore. Okay, so you get better results than that one. It's just have to test it. You just take the models and tell us, I need to have the calculation according to these models. Okay, and then you calculate the volume. You know the total pore volume, okay, by gas absorption, by the absorption term, and you get the cumulative pore volume here by the models, and you can see which model is. Just compare.
And we choose the best fit.
The best fitting, yes. Okay. Any more questions on this? Okay, let's see here the density, energy. Okay, again here we can have the energy also. That's the heat of absorption. Okay, well, there's no models, but because we don't have any models. If we don't have any models, it does not know how to calculate it, okay? The first thing you have to do is download the models. It's very important, okay? We have 7 different models. As I said, we have a guy only work on this.
Why the software, even if it's new, doesn't come with the models preloaded? Of course, we can download later on new models that come after the software. But when you release, I mean, a new software, for example, it was released 2 weeks ago, let's say, it's 5.02. Why doesn't include all the models that are till now?
I can tell you why. Because, well, I'm going to say something maybe you don't like, but I'm going to tell you why. Because we have some country which banned, we cannot sell. And we're afraid that is they sell the instrument, for example, we don't sell to Iran, okay? And we found out some places they bought the instrument and they sent it to Iran. Then we need to know where the instrument is before we release all of our information. This is why. Okay? So now we said you need to register, and you said the AUB, so we know you are from here, and we are going to make some research and to know the instrument is here. Okay? But now they know because I'm here, so we know the instrument is here. Now you have access to all of information. I'm going to close this because I don't want to have a. So let's continue with this. I think this is the only things. This is how to adjust the limits and things like that. Now let's see if we start from the beginning. How can we start with analysis? Okay, so I'm going to get out from here. Okay, so the first thing is file always. Once we get, one instrument, one program, all of our instruments are the same, very close. Okay, so you get a new sample. You have 3 options: physical absorption, chemical absorption, or dynamic analysis. In this case, you don't have dynamic analysis because you don't have TCD. So physical absorption. You have 2 options. You can replace your new sample by another sample done very similar way. For example, zeolite. Next time, she will only have to change the small point at the beginning but you can copy the same thing, so you don't have to enter all the data. But I want to show you how to enter the data. Okay, the first thing is the sample. Okay, you select the sample and you set your name, the name of the sample, whatever you like. Then the operator who's going to operate the system has to put his name. Okay, just in case there's some failure in the system, people know you ran the sample last night and you know who it did. Okay, and the submitter, if it's not your sample, somebody else, you can tell who gave you your sample. Okay, all the sample must be calcined. This is one of the conditions. All the same. Why? Because if you degas your sample or you put high temperature to your sample, the sample is going to release some ions from the salt and it's going to block all the valves. Okay, make sure, and then no way you can clean it. You have to send it back to my States and take it the whole manifold out, or maybe have habit for 1 month here, changing the whole thing. So it did happen to us. Okay, so some customers just put uncalcined sample and heat it up to 400 degrees, and all the salt blocked the whole system.
She was asking me, but if she calcine her samples, maybe it will defect her sample.
It will be ruined. Some samples cannot stand high temperature.
Within the thermal stability of the sample.
If that's okay, because when you go to liquid nitrogen temperature, it's going to freeze down the sample. It's nothing going to release. It's when you heat it up. If your sample is not calcined, like a catalyst, then you cannot heat it up in the system. Okay, you can heat it up outside. Okay, the degassing. Okay, the degassing. You cannot degas the sample in situ inside the system. You can degas it in the degas machine, but not inside the system. Okay. All right, the sample tube. You can, because you have different shape of sample tube, just some of the people, they have different shapes. You can tell the system what kind of shape you have. But doesn't matter because the system measures the free space, measures the volume of the sample tube. So it's just for your indication what kind of sample tube you're using. The classical one, we have that there, okay? The sample weight has to you take it after analysis, because you can degas the sample and put it there, and when you start desorbing the sample even cleaner, so you take the sample weight after analysis. You don't care now you put 1 gram, you can adjust the sample weight after.
So you just remove the sample, the cell, and remove the sample, and measure it, sorry.
What I do, normally I take the empty sample weight clean and dry, the weight, you weigh it, okay? And then you put your sample, more or less according to the formula the one. You don't care if it's 50 milligram or 49, just approximate size. You put your sample, you degas it, you run your analysis, and you finish, you take the weight, and you weigh the sample tube. You know the empty, you know you have the, but difference you get the sample weight. This is the way you have to do it, okay? All right, then.
And they just put the new sample mass here, and everything will be adjusted accordingly.
Yeah. So after analysis you finish, you come back to the file. Okay, you open it and you put the new sample weight, and everything will be recalculated in a few seconds. Okay. Okay, the density. Why do we have the density? Remember yesterday I told you that you can have the empty volume, so you can use it over and over again, because you're using only 20 or 10 milligrams of sample, very small. But sometimes I want to know exactly what is the free space is. Then you get the density, you have the weight, then the instrument automatically will measure the volume and subtract the volume from the empty sample tube. But as I said, it is maybe less than 1% error. You have more error weighing the sample than the volume of the sample tube. So if you take the empty sample tube volume the first time and you said this is A and the volume is 25, you can use it, unless if you're using too much sample. Then you're using too much sample, then the volume is already now important. Then you have to measure the free space. But if you take 5 or 10 or 15 milligrams, it's not going to change too much. So you just tell the instrument, this is your volume, so the system will avoid to measure the free space again, because this is about 1.5 hours, okay? And also you're going to expose the sample to helium. If you have a micropore, the helium is a problem. So in this case, you avoid this problem. So only when you like to enter this, you enter the density, otherwise you don't care. Okay, you can put here is automatically. Why you have manual enters, okay? Manual enter because you can get data from the Quantachrome, for example, okay? And you like to see how is this reduce the data by Micromeritics. So you can enter here the pressure and the volume absorbed, and the software will calculate everything for you according to our programming. This is how manual entered, okay? So you enter the pressure and the volume. Otherwise, it's automatically collected, so the system works automatically. And you can put comments. You say, for example, my sample has been degassed at 400 degrees C, whatever you like to put here. Okay. The degas condition. This is have two ramps. You can see the first one and the second one. Yesterday I told you how important is the degassing. Go to 80 degree or 85 degrees C, 10 degree per minute, and stand it for 30 minutes. And then second one you can go to 400 degrees C. What is the maximum temperature? Is the calcination temperature. Is the temperature at which your sample has been calcined. Okay, not more than that. Otherwise you're going to decompose the rest of the salt. Okay, so you can have two ramps to do it here. No problem. Analysis conditions. Here, yesterday, this is a new program. I did not know too much. I had to call my states to tell me how you do it. But the professors here, he know how to do it. It's better than me. Okay, so you start from the starting point, you start 0 at very high vacuum. Then you get increment, okay, and you get here 0.05. We didn't know anything about the sample, okay, we just 0.05. But if you need to get more points, in this case, you have to put 0.01, for example, to get more points, okay. So we get 0.05, 0.05, okay, and then it tells you the first point is this one here. So what is going to have?
Sorry, did you turn the microphone on again?
Huh?
Did you turn it on again?
Microphone.
I don't know. Do you have the microphone? It is. It is on.
It's on, yeah.
It's on. Why you said this?
Because I thought you turned it off before.
No, I just put it here.
Oh, okay.
No, because if he doesn't know, he would tell me.
The degas station, the temperature cannot be programmed to stay for 30 minutes on 80,
Yes,
then to jump,
of course.
so that we don't interfere.
No. It's everything automatic. You just program it and you leave, and the sample is by automatically done. Okay. Then you can select, for example, here from one point, another point is small increments. You have dose amount or you have pressure increments. Okay. In any case of these two, you need to have an idea about the volume absorbed by the sample. As I said, you measure 1 point and 0.3, and then from the volume, you can get from the pressure or from the volume how many points you want to have. You divide, you get 100 milliliters up to 0.3. And if you have 100 points, you put those 1 milliliters, so you can get 100 points. Okay. So in any case, the pressure or the volume is the same. You can get here the equalization time. As I said, this default is 5. You see, I did not do anything. It came 5 seconds. 5 seconds, so fast, because my son and other people didn't know anything about it. Okay, so you have to put 15 seconds for Mesopore and 45 seconds for the Micropore. So you can go to the second here. You can append and the second point from this point to another point. If you have a Mesopore samples, then you go for Micropore 45 seconds, and for Mesopore you can 15 seconds. So when you finish the Micropore, it goes faster for Mesopore. So you have this to select during adsorption and during the desorption. Okay. So from there here you have the pressure table. You can insert or you can just append and change here from there to this one here, and you can say whatever you like to select here. Okay. But we should not do it blind. We need to have an idea about the volume absorbed. Okay, the free space. The free space you can measure. If you measure the free space before the analysis, the system has to lower the door. Why we have to lower the door? The free space is measured first at room temperature, then it raises the door to measure the free space at 77 K. So the helium can be trapped. The pores, some of the pores are fragile, so they shrink and absorb, and not absorb, but they hold the helium inside. They trap the helium inside. Okay, we need to lower the door to warm up the sample. So you open the pore, so all the helium comes out. If the helium does not come out, how do we know? On the first portion of the adsorption after at very low pressure, you're gonna get something like this. Nice. Okay, so it's bad because it's helium. As I said, the pressure, the volume cannot go up, back. You have to go up all the time. Okay, so you have this option, and then you have to select that time for the evacuation is 0.2, too low, 0.1. You have 0.5 at least, half an hour. Okay, so it's typical 0.5. You can measure free space. This is just if you have the number, you enter it here, or you can enter after analysis. Here, enter after analysis. Then it will continue doing. We don't expose the sample into helium as we did yesterday. Okay, we measure the free space after analysis. Okay, the free space is measured by helium pure 99.9999 non-condensable gas. Okay, if you have oxygen, it's going to condense at 77K and you get a problem. That's what we got here. Okay, but you don't care because it does not change the volume. Okay.
So Simon, if we already have the empty void and the empty space, we can just put it here,
Yeah.
the number, and
Yeah.
we skip this.
Yeah, you just enter, the system will skip.
Only if we use
You'll have the empty, you have the warm and cold.
Okay.
Okay, because every time you finish the analysis, it will show you the warm and
We
cold.
run it once, and we can get to the values. And if you use
Yeah.
the same cell again, we can only input
It enters here. That's
So
it.
every user has his own. He has to buy his own cell.
only in case of large masses we have to take into consideration the difference. يعني in case 50 milligram it can't work.
The 50 milligrams depends on the density. Okay, some of the sample, because there's very large porosity. Okay, then has a lot of volume. So
Up
yeah,
till 30 milligram we can apply.
I said 20,
Up till 20.
20 milligrams. Yeah.
Aslan, most of our materials are porous, so we don't need to go up 20 milligrams. As for sensitivity for them.
Yeah, but it depends on surface area. How much the surface area is to see what.
Usually muffins is high.
Morphos is 10 milligrams, 5 milligrams is good enough. So you see the 5 milligram, even you have to look like under the loop so to see what it is, the sample. It's a very small amount of sample. So that volume is maybe the error is 0.0005%, nothing. So it's not worth it to lose 2 hours measure free space in this case. Okay, but it's up to you. I'm giving you all the options and you select whatever you like. Okay,
I have a cell that doesn't have a bulb.
doesn't matter,
It's a thin one. That's okay. I can use it.
no problem. Okay.
Thickness of the rod.
As long as the O-rings fits around it,
Yes.
no problem. So we don't have a leak. You can test it empty. Okay, you put the O-ring there and you apply a vacuum to it. Okay, for maybe 10 or 15 minutes. You close the vacuum and see if it's holding or not the vacuum. Okay, if it's holding, no problem.
It's the same diameter. It will be okay. 12 millimeters.
No problem. Okay, the P0 and T. Okay, it is very important to have many options. The best option is to measure the P0 every 30 minutes, for example. Okay, why? Because I said the P0 depends on 2 different things: atmospheric pressure and the purity of the liquid nitrogen. Okay, the purity of liquid nitrogen, maybe 10 hours or something, does not change too much. It will not absorb too much oxygen. Okay, if you expose the liquid nitrogen to air, it will change the temperature very fast because it will absorb the oxygen. Remember, the oxygen is 10 degrees below the liquid nitrogen. Then you can see it. The liquid nitrogen, the colors change into blue. Okay, and if the atmospheric pressure change during the winter time, is good to measure it. So it does take a few minutes only, but it will give you correct numbers. Remember that the size of the pore is a function of the relative pressure. If your relative pressure P over P0 is not correct, your size of the pore is not correct. So let it measure, okay? Measure it, and at 77K. Okay, you have to tell us this liquid nitrogen, 77K. Okay. What time is it? 12:30. What time we have to break?
No, maybe we can stop after 3-4 minutes maximum.
Yeah, we're gonna finish, okay, here. The dosing is exactly the same as the increment pressure. Okay, you can dose 3 cc every time. So in this case, is set to get the pressure is going to dose amount of gas 3 cc, equilibrate, and see what the pressure was. So instead of put pressure into volume to measure dose the pressure and get the volume. In this case, dose volume and get the pressure. So whatever you like. Termination is very important to fill up the sample tube with nitrogen because it's under vacuum. Okay, sometimes the people push it like this under vacuum, you break the tip. Because if you push it straight, it's okay, but sometimes they take it like this and you break the tip. If you break the tip, okay, you can still using it. You can cut it, okay. Because the system measures the free space, measure the volume. Okay, you cut it. So I saved you some time and some money. Just cut it nicely. Okay, and the system will measure free space, and the downsync will be shorter. Okay, shorter means that it has less life during analysis because the thermal jacket is going to be shorter. okay? But it keeps working. Another thing before this is finished with the system, how we set up the sample is very easy. Okay, once you set up everything, so you go to unit number 1, you go to sample analysis, and you browse. Okay, you have 3 different ports. Okay, you browse. You said, okay, in number 1 I have sample A, number 2 I have sample B. So you can have different conditions to different samples, but you have to listen to where it is. Okay, for example, the first one is micropore, but if you put the micropore in session number 3, it's not going to do micropores because we don't have the micropore option. Okay, so you have to select the correct ports there. Before we finish with this thing, so only 1 minute, is the isothermal jacket. It's very important to use the isothermal jacket dry. Okay, just put it inside the sample tube, on the sample tube, and push it all the way down. Okay, what it does, sorry, that the liquid nitrogen level, you should measure the liquid nitrogen level with a T. Okay, the black T you have there. Okay, you have levels, so you don't overfill the system. Why? Because if this is my sample tube, okay, and this is the isothermal jacket is up to this point here, if put more liquid nitrogen, the liquid nitrogen in a few minutes is going to drop a little bit. And remember, 1 cc of gas at 77 will transform into 500 cc at room temperature. You break the tube, pop, go in the tube, okay? So never overfill this. Now, if you have the isothermal jackets here and the level of liquid nitrogen goes out from outside down, doesn't matter because the nitrogen is going inside the isothermal jacket, is going for capillary ascensions, going inside and evaporating here. We mean this is the sample tube volume is constant even though the level of liquid nitrogen is going down. But if it goes below the isothermal jacket, it's going to explode the tube. If it's empty, no problem, but if it has nitrogen, then the volume is going to expand and it's going to explode the tube. The problem is by explosion of the tube, it goes so fast it will break the sample, the door. The door is very expensive. Okay, so your door can last for at least 36 hours. Okay, none of the analysis should last more than 24 hours if you take the correct sample weight. Now, for example, in your sample, you have 1,000 meters squared per gram. Okay, and you take, for example, instead of 5 milligrams, took 50 milligrams. It will finish next week. Okay, then it will finish next week. Then you have to refill the door, or if you don't refill the door, you will have a problem. You will break the door.
Sorry, if this is the same sample, you put 50 milligrams instead of 5, it will take this time?
Yeah. Yeah, it's going to be 50 to 0.005. How much it is? It's 100 times more. So you have 100 times more time. If the time was, for example, 10 hours, multiply 10 by 100, it's directly proportional to the sample size. Okay, so this is almost 1 week or more.
Once I've done the ZIF 8, it has high surface area. I put around 30 milligrams. It took more than 12 hours.
Yeah.
We put it at 7 first day. We came next day at around 3, 6. It ended afternoon.
Try to put enough sample, but not too much sample. Okay, so that first it goes much faster. And secondly is that if it's the liquid nitrogen level, because it's very difficult if you like to refill the door, it's difficult. It's not that easy. I understand this because you need to lower a little bit the door, a little bit only like this. And you have to have a special funnel, okay, like this to go inside. Then you have to pour liquid nitrogen and then you have to measure it. So bit by bit, you have to measure it because if it goes above, then how do you take it out? So this will have at least 36 hours. If it's well covered, the system, you should not have any problem. Secondly is the cover. The black cover on the top is very important to really be there, okay? Because the door is going to go up, it's going to close. So it's going to push the foam up so that avoid any condensation. Okay, if you have here, you have too much condensation, you have ice around it, okay? So when the finished analysis, the door is going to come out, down. And if you have ice around the sample tube, it's going to push the sample tube also down. Okay, this is why you have to use it very well and sometimes using down and up and down for sometimes the foam just because deformed. Okay, is bad. You have to change it. Okay, it should close perfectly on the top. I think that's it.